So what I'm going to talk today is a particular component of the proof of black hole decay theorems, which I will actually start by, oh, damn it. Of course it is. I will start by formulating the theorem. Yes, well, but now you can't see, I suppose. I'll start by formulating the theorem and then explaining how the theorem fits into the whole decay framework. And then we'll go towards the proof. So here's the theorem. So it's due to many people. I will have to fill in the details as we speak. The theorem is something called the upper resolvent bound. So here's an estimate that I'm going to be proving. Obviously, I will have to explain what all the components are. So what we have here, I will first present this thing as a pure fact in semi-classical analysis. And then, of course, I'll have to explain what these operators are. Well, this is a L2 to L2 bound on a norm of an inverse of an operator. Now, what are all these objects? Well, so the operator P is a semi-classical pseudo-differential operator. A particular case would be a differential operator where you put the small parameter h next to every differentiation if this little p was a polynomial. So I believe Andras Vashi gave us a mini course where semi-classical calculus in particular was introduced. And my assumptions will be that this operator is self-adjoint. And for simplicity, just for simplicity, I will assume that it has principal symbol of order 0. OK. Now, the operator Q, which has the imaginary component here, this is something called the complex absorbing operator. I will also assume it's a semi-classical pseudo-differential operator, also self-adjoint, also bounded symbol, and I will assume that the symbol of this operator is non-negative. So it's a specific sign of the imaginary part of my operator. And then here the conditions on this lambda would be that the real part of lambda is O little of 1, so smaller than some epsilon. And the imaginary part of lambda is bigger than minus nu h. So what happens here is really I'm looking for an estimate on an inverse of a family of operators which depend on a small parameter h. And then the estimate is only true as h goes to 0, so for h small enough. And then my lambda is in this box. Here's my real line. So the horizontal part of this box is small. And I assume that my lambda is not too deep. So this is going to be the key restriction. Namely, I can say that I have a spectral gap for this operator. If I didn't have my Q, I could say that the spectrum of my operator lies below the strip. So I have a strip without the spectrum. So this is something called a spectral gap. OK, so this is the abstract setup. Of course, this estimate is meaningless unless you specify conditions. So this is not always true. This is true under a somewhat elaborate set of assumptions. Or you specify where you intend to use this estimate. Well, so as I have disclosed before, this estimate comes in as an important component in proving statements about decay of linear waves, just like the statement that Michalis just showed on his slides in the previous talk. These are statements of the form, if you have a localized, so if you have a solution to the wave equation on the exterior of a black hole. So I will not speak too much about particular black holes because I want to present an estimate which is true under certain abstract set of assumptions. And then you want to ask, how fast does this solution decay as time goes to plus infinity? So what was known after a rather elaborate series of works by many people starting from the Fermi-Srodnyansky and culminating in their paper with Schleppentock-Rothman, and of course many works by other authors which were already mentioned before, is that if you take the exterior of a Kerr black hole, subextremal Kerr black hole, then the decay here is polynomial. However, the fact that you have polynomial decay for wave equations in exterior black holes is due to effects which are beyond the scope of this talk, which have to do with spatial infinity. What we do today is we consider the effects that come from having trapped trajectories, so trajectories of light that do not cross the black hole event horizon, that do not escape to infinity. And decay coming from these trajectories is always exponential. So one way to see this exponential decay would be to take a positive cosmological constant. And that was done in particular also in a large body of work, in particular including Boni, Hafner, Vashi, and some of my own work, which shows that a certain norm of this solution is actually decaying exponentially as time goes on. So to have a theorem like that, there are certain catches, again, none of which have to do with the phenomena of trapping, so I will sidestep most of them, but legally I have to say, either you take a positive cosmological constant and you ensure that you have no low frequency resonances in the upper half plane, so that's a separate question, or you can take the zero cosmological constant and you can consider high frequency solutions. And then this will be a somewhat conditional statement because this will only be a statement about the high frequency part of your solution. One way or another, this resolvent estimate should lead to having exponential decay of all of your solution or not, depending on whether you're able to handle the rest of the problem. And these two numbers that occur here are very important for this estimate because the number nu, up to which you can get the spectral gap, determines the rate of exponential decay, modulo small epsilon, and the exponent here in the estimate actually tells you how many derivatives you lose in your decay statement. So here you will have Hn on the because this is the right-hand side problem. Yes, exactly. This is the same n. So as Michalis pointed out before, a classical work of Ralston, which was extended to this setting by Zbierski, tells you that if you have at least one trapped trajectory, this n cannot be equal to 0. You cannot have a non-trapping estimate. You cannot have energy boundedness or energy decay, even in a compact set. However, for the kinds of trapping that we will consider, you will have decay with loss of derivatives. And this exponent tells you how many derivatives you lose. OK. Now, and I should also say that if you want to start with this estimate and you want to arrive to a statement like that, say for Kerr de Sitter, what you would need to do is you would need to plug in, or rather you would need to start with analysis of Vashi on the event horizons and the rest of the contributions of the problem. And then you can glue this estimate with the absorbing potential with the results of Vashi using the methods of Dachev-Vashi. OK. So from now on, I will concentrate on this particular estimate. And I will explain a model case of why it is actually useful without going too much into the details of how to plug it into a specific black hole. So a basic case would be if you take a manifold, which is, imagine you just have a product structure, and you just take a manifold which is an outside of a compact set. This is the simplest, most easy to write out, at least. So you just have a compactly supported metric perturbation of the Euclidean space. And then, of course, you can consider the wave equation. And what happens, how do you reduce this estimate to the estimate on the resolvent? Well, if you Fourier transform your wave equation in time, you will see your parameter lambda here. And then you multiply everything by h, because what you want to do is you want to estimate the resolvent at high frequencies. This somehow turns out to be the part of the problem that involves trapping. So for this case, what you would do is you would take your operator p, which would be h square root of Laplacian or negative Laplacian, depending on your convention. So this is a semi-classical operator, not bounded, but the symbol here is just absolute value psi. Now, if you consider the wave propagation, you can just write it in this form, e to the minus ITP over h. This is a funny way to just write, well, a portion of the wave propagator. So where does this q come in? Well, you need to have some kind of control on spatial infinity, because you start with some wave. And what happens as this wave propagates for a long time, you need to know how it goes to infinity, because various funny things could happen at infinity. What you can do instead, if you just want to analyze the phenomena of trapping, as I said, and there are situations where this can be reduced to this estimate then, is you just put your absorbing potential here. And then if I formally write it out, of course, they don't commute, but morally speaking, this just has this form. So what's going to happen is my absorbing potential will be required to be strictly positive. So the symbol will be strictly positive near the spatial infinity. And then if I can draw a picture here, if this is the part of the space where I did my compact perturbation, or for a black hole, if this is the part of my space where trapping is. So outside of this part, I have some kind of non-trapping control. Then you put complex absorption outside of this part. And then you can see that if you have a trajectory that escapes, example like that, in positive time, rather than controlling for all positive times what happens with the propagation of this trajectory, we just dampen it here. So as soon as this trajectory reaches the support of the complex absorbing potential, it's killed. So that makes for a simpler estimate in terms of it's simpler to handle the infinite ends because you just dampen them. So you can concentrate on what really happens in the trapping region. Now, I should also point out that, of course, in a way, this setup is closer to what you can get in reality. Well, who knows what reality is? Of course, the real absorption is more complicated than just adding a potential like this. But I should say that, for example, I was accidentally in the same laboratory in Nice as Maciej Zworski on Thursday. And what they do is when they set up a scattering theory experiment, they do not let their system go out to infinity because you have the walls of the lab. Your waves will bounce back and create effects that you really don't need to see. What they do instead, they actually put absorbing materials at the boundary of their box or at their triangle. And that creates the same effect. Similarly, for black holes, I think we're all happy with the fact that our world is not a small perturbation of one black hole. In the sense that, well, we're very happy that Earth is not a small perturbation of a black hole. But what is also important, of course, if you have a black hole, you have stuff falling in. So as you have waves emanating, gravitational waves emanating from the black hole, they pass through this matter, and something happens to them. So to some extent, they might be absorbed by this matter. It's, of course, not very easy to have a physically realistic picture of that. But what I wanted to say that this absorption, while for us it's a convenient device, is also quite apparent in real physical models of what would actually happen. OK. So now, let's see. Of course, I didn't write the whole theorem, and not just because I didn't write the names. I will write in the names. But this kind of resolvent estimate depends very, very much on what the structure of the trapped set is. If I just leave it like that, that's just a completely false statement. You can think, well, if I took my q to be 0 and I took my estimate on a torus, for example, that's definitely false. So what we need to exploit, we need to make some assumptions under which the theorem will be true. And these assumptions should also hold for the black holes that we're studying, in which, in our case, these are subextremal Kerr and Kerr de Sitter black holes. But first, let me define what I actually mean by trapping. So as I said, once you reach the part where your absorption takes in, you're essentially damped. You will never see this trajectory again in the asymptotic regime. It will produce a very, very small contribution. So a natural thing would be to define something called incoming and outgoing tails. So the outgoing tail are trajectories which in the past never pass through this absorbed region. So these are just trajectories in the cotangent space of my space slice, which is M, such that if I go backwards in time, I will always stay in the place where my q is equal to 0. Maybe I should write it like that. Also, a technical condition to not lie too much. You should lie probably in your thoughts, but you shouldn't lie too much. That this operator is very easy to invert in the places in phase space where my symbol is not 0. So I can say I can intersect my trapped set with a small energy shell. That would make these statements more correct. Now, so this is my gamma plus. So these are these trajectories that when you go backwards, they never reach the absorption. So these are the problematic trajectories. Well, some of the problematic trajectories. Of course, you also have the opposite situation, this gamma minus, which are trajectories which are trapped in the future. So I can just put it here, and then plus minus. And then there is the trapped set, which consists of trajectories which are trapped in both directions. So here, in this picture, it would just be this point, and all the other trajectories in the picture that I'm drawing would be non-trapped. Yes. I guess I have to correct myself here. I have to. Since I'm at energy 0, I should subtract 1. So here you really see if this is like 0 and h is small, then I'm really looking at the spectrum of this Laplacian at high frequencies. OK. So as I said, it depends very strongly. Your ability to show resolvent estimates and to have exponential decay depends very strongly on what the geometry of the trapping is. And the geometry that we will consider here is something called normally hyperbolic trapping, which has this very nice feature that if you start at a trajectory, if you started at a trapped trajectory, you would think that you could construct a solution to your wave equation which just lives on it forever. However, what happens since the solution blurs out as time goes on, because it is, after all, a wave and not an exact particle, most of the neighboring trajectories will actually be escaping. So most of your solution will escape as time goes on, and the part that stays will be exponentially small. That's, I guess, a physical explanation of what's going on. Of course, the question is how to make it into a mathematical statement. And that's what we'll do with these assumptions. So this set of assumptions is called normal hyperbolicity. Good enough. And these are assumptions which are very rare. If somebody gave a talk and was giving a theorem under these assumptions, my first question was, why are you doing this? Because it turns out that for most scattering theory situations, they do not hold, even the first one. However, what is very nice is that they do hold for black holes. And so that is what we're going to exploit. If you want, we're going to a very, very particular trapping situation, but we're extracting a lot of information out of it. So the first assumption already is ridiculous in most situations. So by the way, so my stable, unstable tails and my trapped set, they all live in the phase space, which is the cotangent space of the space slice. And then when I say dynamics, I mean the Hamiltonian dynamics of the symbol of my operator, which in that case would just be the geodesic flow living on the cotangent bundle. So the first assumption is I assume that my incoming outgoing tails are smooth, orientable. That's not that ridiculous, actually. Hypersurfaces. So codimension 1. Here. This is already quite rare. You take 3 disks. You take scattering on 3 disks. These have fractional Hausdorff dimension. They have no chance of being smooth. However, in this particular case, they are. Next assumption is that they intersect transversely. And their intersection is, well, it's codimension 2. I assume that their intersection is symplectic as a submanifold of the cotangent bundle. And finally, I have to assume something that's called normal hyperbolicity, which is just this. I'm trying to say that my trapping is unstable in the sense that if I start a little bit off a trap trajectory, I most likely will not be trapped. And it works in a way of having a stable, unstable decomposition, but only in the directions transverse to the trapped set. So at each point, if I take the tangent space at k to gamma plus minus, so k is a codimension 1 submanifold of gamma plus minus, it splits into the tangent space of k and some invariant, smoothly depending, one-dimensional subbundles. And if I take the Hamiltonian flow, they're restricted to this. It's going to be exponentially decaying. If I go in gamma plus, this is going to be in negative direction. And if I go in gamma minus, this will be in positive direction. It is easier to illustrate this by a picture. So if I find my eraser, perhaps I can do a picture here. Erase this model case. So the picture of the dynamics is like that. Let's say I take gamma plus. So gamma plus is trajectories that are trapped backwards. This is a surface. It's invariant under the flow. And then we have k, which is a codimension 1 thing there. The flow is tangent to k. And the point is, as you leave k, you should really diverge exponentially. So if I took a trajectory on gamma plus and I went backwards, it has to exponentially converge to k. Now on gamma minus, you would see the opposite situation, like this. So what I draw here as a 2D thing are these lines. So I drew my k as a point, but of course k is a codimension 1 submanifold, so it has a lot of dimension. That's how I manipulate it. And what is more is that, in fact, I also want to specify, it's kind of written in a very small print here, but I want to specify the minimal rate at which this exponential convergence to the trapped set happens. Now, that's the assumptions that we make. And then there is another assumption which is not needed for the theorem here, but is needed for two other statements. So I will make it here in kind of a box. I will just briefly talk about it. So there is a stronger assumption that is also useful. It's called R-normal hyperbolicity. What this is that you assume that your minimal exponential expansion or contraction rate in the directions transversal to the trapped set actually dominates a lot. So here R is fixed constant, but much larger than 1. The maximal expansion rate along the trapped set. So the trapped set itself is a manifold. The flow is tangent to the trapped set, and it has the maximal Lyapunov exponent. So for a Kerr or Kerr de Sitter black hole, the flow is completely integrable and has no hyperbolic points. So this mu max is just equal to 0. And there is no expansion. But of course, in other situations, there might be. And this is the assumption. This assumption helps us in two ways. First of all, this whole set of assumptions together is actually structurally stable. So if you take a perturbation of this setup, you will still arrive to smooth, well, here I have to replace C infinity with CR then, so to sufficiently regular incoming outgoing tails. Without this R normal hyperbolicity assumption, you can start normally hyperbolic trapping, perturb it a little bit, get something fractal, to which the result would not apply. So because of this fact, which was proved by Hirsch, Pugh, and Schub in 1977, you can see that this result will be stable under perturbations, just because the assumptions are. The other reason why this is useful is because this lets us exhibit further gaps without resonances, but I'll talk about it a little bit later. All right. So now, these assumptions are, as I said, valid for, I can write it here. These assumptions are valid for Kerr, the full subextremal range, and Kerr de Sitter. So that requires some verification, which is, it's an exercise in ODE theory, if you want. And Kerr de Sitter, also full subextremal range, well, for small values of cosmological constant. There could be some weird cases. So for example, what would happen for Schwarzschild is that this point would be the tangent space to the photon sphere. And then this gamma minus would be trajectories that exponentially approach the photon sphere and wind around it as time goes to plus infinity. OK. Now, the theorem that I want to state is, I guess I have to pull this down again. So now we have our assumptions. They are laid out there. We have our motivation. And now we should have our result. So this theorem is due to in different generality, which I'll have to talk about. Josh is found in 88. Wunsch, Zworsky in 2010. Nonnemascher Zworsky. Zworsky, 2013. And the version, the proof that I'll present is myself in 2014. So what does the theorem say? Well, it says that under these particular assumptions on the structure of trapping, you do have a spectral gap. The size of the gap is given by, again, modulo n epsilon, so for each epsilon, half of the maximal expansion rate. So if you want the rate of decay of waves is equal to 1/2 the expansion rate governed by classical dynamics. And here, the constant that you get for this particular estimate is kind of funny. It's O little of h to the minus 2. Yes. So you have two semi-classical pseudo-differential operators. Yes, but, well, the assumptions are here. So the assumptions are on the structure of the trapped set. There are some topological assumptions, because the way I set it up, you could have your k on the boundary where q is bigger than 0. But yeah, that's it. Yes, so all the assumptions are on principal symbol level, except, of course, I assume that they're both self-adjoint. And for q, I guess, have to say q is vanishing near k, because otherwise you could smuggle a little bit of a sub-principal term on the trapped set, and that would shift your parameter. But in reality, you just want your complex absorption to just be completely 0 near the trapped set. Just like in the black hole case, you don't put absorption on the trapped set. OK. Now, I should say, before I go on to examples and proofs, I should explain what's the difference between these 4 results. So Girard and Sjöstrand proved this statement with no polynomial bound and in the analytic category. So they used the methods, they did it for analytic operators, and the bound they would get here would be exponential, which is not very efficient for a purpose of obtaining wave decay. Wunsch-Zworsky did this in a manner that would be useful that is useful for black hole decay, however, without recovering the precise size of the gap. So they just knew that the asymptotic size of the gap is some small number. Of course, I should also say that the actual rate of exponential decay might be governed not by that, but by low-lying resonances. But that's not a phenomenon we're considering for this talk. And then Nonnemascher-Zworsky, in a much more general situation of contact ANOSA flows, showed this gap, so following earlier results of Tsuji and Ford-Tsuji in this setting, and how they managed to get a result that applies both to ANOSA flows and to black holes. Show the optimal size of the gap, but not the optimal rate of, not the optimal loss of derivatives. And I should also say that the proof that I will present is in many ways more elementary than the previous proofs, albeit it does not apply to the more general situation of Nonnemascher-Zworsky, and it does not apply to ANOSA flows for more than one reason. So somehow the assumptions are too restrictive for that, but it does apply to black holes. And then I should say that, in fact, there are further results in this direction, which is, I should say, further gaps. So I will definitely not have time to talk in detail about these results, but they are nevertheless quite interesting because this is something that's very rare in resonance theory, how the first gap is known in many situations. But what you can actually show in this case, that not only have your first gap, which is given by modulo epsilon, half of the minimal expansion rate, but then you have, under a certain pinching condition, you have a whole band of, you have a second resonance-free strip, which goes from half the maximal expansion rate and 3/2 the minimal expansion rate. And then you have further gaps like that as long as pinching conditions hold. And what is more, at least in the first band, you know that you actually have a while law for counting resonances. So one particular result, one particular consequence of this further gaps and while law, it tells you that, in fact, you did not miss with your optimal decay rate, that in fact, there is a lot of resonances which would give you, each resonance gives you a solution to the wave equation which decays exponentially at a fixed exponential rate. So it prevents having faster exponential decay. And you have actually lots of these in this strip. And these are just given, these depth of this band, and so on are just given via natural dynamical quantities, which are the minimal and the maximal expansion rate across the trapped set. Then I should say that in the context of ANOSA resonances, which is of ANOSA flows and Paulikov's royal resonances, which is different technically from the one employed here, however, bears a lot of similarities in the inside structure of the trapping. Ford and Tsuji obtained similar results with, again, bands and while law. OK. So now let me raise the board. Finally. Sorry. What's so cold in this room? I don't know what happened. Yes. I guess when you start moving and talking, it varies. So now, that's the result. As I said before, it gives you, under these dynamical assumptions, it gives you both the optimal rate of exponential decay at high frequency and how many derivatives you lose. That might be not optimal, but should be getting pretty close. Now, let me give two examples, which I will try to convince you. The first example will convince you, hopefully, why this applies to black holes. And the second one might convince you why this statement is true. Of course, the trick is the examples are not the same. So here is a useful example. So I thought that with all the abstract jibber-jabber about semi-classical pseudo-differential operators, I should write at least some concrete example of where the thing holds for people who don't spend their days and nights studying semi-classical quantization. So here's D is 1 over I partial. So if you take the semi-classical Schrodinger operator, and then my potential is a barrier top potential. And the barrier top, let's say, just touches at 0, like that. Now, how does this come up in black holes? Well, if you separated variables for your Schwarzschild curve black hole, you would see an operator exactly like that. And you would then have some lambda, which would correspond to the separation constant by spherical harmonics. Of course, I should point out that this theorem doesn't really rely on the symmetries of the problem. It's just easier to demonstrate this way why this has to do with black holes than me writing out the whole three-dimensional system. So if you look at, so this is my potential V. If you look at the dynamics, what you will see, so this is a person standing on a hill. So you will have, if this is x and psi, my symbol is given, so it's a function of position and momentum. It's given by psi squared plus V of x. Then the Hamiltonian dynamics, well, it's just dynamics of really a person standing on this hill. So you will have lots of trajectories which are not trapped. There's person rolling over this hill like that. OK, that's not a very nice way to draw it. Person rolling over the hill the other way. Person not having enough energy and kind of just rolling back from the hill. But then there are the interesting trajectories. There's the trapped trajectory, where you just stand on the hill. But it is, as you know, very unstable. Well, on the real hill, it is stable because you have traction and you have stabilization. But if you didn't have that, you would most likely start falling. So you can fall along these incoming and outgoing. And you can verify that the assumptions, they are satisfied. Okay. Now, here's another example, which is a conceptual example. It's kind of hard to explain how to fit it in a real problem, but then you'll see that the dynamics is the same, and that example can actually be analyzed. I'll just take this operator. And then I add this constant, because otherwise it's not going to be self-adjoint. So that constant is what's going to bump my thing, actually. It's just x times partial x with funny scaling and plus 1/2. So if you look at the symbol here, it's x times psi. Well, what's the Hamiltonian dynamics? If this is x and this is psi, the Hamiltonian vector field is x partial x and psi partial psi. So what you see is the hyperbolic flow, which looks like that. So this is my trapped set at 0. And then my outgoing tail is psi equals 0. And my incoming tail is x equals 0. Now, what if I wanted to actually understand resolvent estimates for this problem? Well, I did one wrong thing. I did not put in my absorbing potential. I should say that the proof doesn't really use an absorbing potential as much. You just need a device to enforce a certain microlocalization condition on your solutions. And this device can be either control at infinities or at event horizons, or it can be this potential, in which case the paper is easier to write up. So what this absorbing potential does is, remember when you have a solution, it's everything that reaches this q bigger than 0 is just killed. And then you propagate for a long time. So if you started with a solution in some ball, and then you propagate it for a long time, what will happen is the solution will elongate along gamma plus. So this isn't the mathematical way to prove it. That we'll reach in a moment. But it turns out that OK, I think that's enough. It turns out that if you, in fact, this would be step 1 of the proof, that if you had a family of functions that satisfy this, and your f was small, so let's say 0 for now, then you would know that your solution is microlocalized in a way I'll also have to define. on gamma plus. So if you want to rule out the possibility of eigenstates for this operator, all your eigenstates will be localized on gamma plus in the microlocal sense. And that's the only place where we use this Q. Now if we go back to this example of a hyperbolic flow, I'm not even going to bother with Q. You can of course put it in, but then it becomes more messy. So we're just looking for places where this operator is not invertible. We want to see, well, what kind of gap we can get. And then, well, this is an OD, so it always has some kind of solutions. However, we want our solutions to live on gamma plus, which means we want them to live at 0 frequency. And what does this mean? Well, the other option, all the other trajectories, so if a solution lived on some other trajectory, it would have to go towards the fiber infinity, which means it would be non-smooth. So in this case, the condition of living on gamma plus, it turns out to be equivalent to u being smooth. And now if we look at this equation and we rescale it a little bit, what we see is x times partial x plus some constant, u is equal to 0, and u is smooth. Okay, so this equation we can solve, right? I hope. In the morning, we could definitely solve this equation. Now, I don't know. After, entree, main course, a cheese, a dessert, and a coffee. But this is an OD, so the solutions are just powers of x. So in this particular situation, you know what's going to happen. Your resonance states, so places where the eigenstates would just be x to the k, where k is at 0, so non-negative integers. And the corresponding resonances will be this. If I draw this, you will have a resonance minus h over minus ih over 2, minus 3ih over 2, minus 5ih over 2, and so on. So for example, a constant function would correspond to a resonance at minus ih over 2. And that's exactly the size of the gap that we promised. And then if you compare it with these farther gaps, you can see that the result is essentially optimal. It has to be. OK. So now that's enough with the examples. I think I have a little bit more than 15 minutes. So I should explain how the proof of this goes. So you can see from this picture, what really happens is we have so much smooth structure of the trapped set of the incoming outgoing tails. You see, you cannot just have some kind of randomly chosen, fractally concentrated solution. Your solutions really have to be stratified by these decay rates. Like here, you would have either 1 or x squared. You cannot have a fractional power of x. That's what is the feature of the problem. Now we just need to exploit it in some way. Now to do that, we start with me lowering the board again. So the proof works in 4 steps, which means I have about 4 minutes per step. The first step is the easiest, in a way, the most standard step from a microlocal point of view. But for this step, I will give a very brief definition. Namely, if I have a open set in the phase space, and then I have a family of L2 functions tempered, defined on some sequence of h's converging to 0, then I say that u is O large of, let's say, h to the alpha on u if this holds. Alpha in L2, whenever support of alpha lies in u. So it's really convenient for me to say that my solution is small in L2, but in some parts of phase space. And what this means is that if you take a multiplier, if you take a pseudo-differential operator with symbol supported in some open set, then you apply this to your family of functions, then you will get something that is O large of h to the alpha, where alpha can be any fixed number. So usual wavefront set is this with the h infinity. So this definition allows me to measure concentration by solution in different parts. So in particular, what we do in step 1 is, how do you prove an estimate like that? Well, you can do it by contradiction. Assume the estimate is not true. Then the estimate is only required to be true for h small enough. So then I can take a sequence of h's and a sequence of counterexamples where it's not true. I will suppress the sequence from the notation. And what you can do, then you can come up with a, if you want, a family of L2 functions, u and f, so that this holds, this equation holds. And then norm of u in L2 is 1, and norm of f in L2 is O large of h squared. That's exactly the opposite of the estimate that I wrote. So if I can show that no such situation can happen, then I have showed my estimate. Now, so the first step in the proof would be to show that u is O large of h away from gamma plus. So complement of gamma plus is an open set in the phase space. So what this means is that if I wanted to measure my u somewhere, let's say somewhere here, so I want to take a pseudo-differential operator that support away from gamma plus, that wanted to apply to u and measure the norm, it would be smaller than you would expect. And the reason is just propagation of singularities. So by propagation of singularities, you can propagate this whole thing backwards because you don't intersect gamma plus. And then somewhere backwards, you're controlled by ellipticity because of the absorbing potential. And your propagation is still valid because the sign of a potential was chosen the correct way. So this is, if you want, the standard part of the construction. That's what confines our trouble-making solutions to these outgoing tails. Which is, again, what you would expect. You have some kind of physical situation. You have your photon sphere. It rings. When you do your frequency analysis of what kind of solutions you get, well, you should have this sphere should ring out solutions. So you should only see solutions which are supported in trajectories that kind of emanate in this funny way from this photon sphere. So it's natural. Now, the rest is less standard. Of course, this didn't use any kind of structure of trapping. That's just a general fact. So what I do need to do now is to really use somehow that my trapping is normally hyperbolic. And the way we do it is step 2. We find an auxiliary equation. Well, so I want to find a certain equation that's satisfied by my u on top of the usual equation, pu equals f. For that, I will need the following lemma. That there exists two functions, c plus, say in c0 infinity of the phase space, such that near k, gamma plus is given by phi plus equals 0, and the differential of phi plus is not vanishing there. So I'm constructing a specific defining function of gamma plus, which was an orientable hypersurface. And, of course, I have to say something about the flow. If I differentiate my phi plus, I get, along the flow, have this condition, where, again, near the trapped set, my C plus is positive. In fact, it's bounded below modulo epsilon by this minimal expansion rate. What it says is the following. So what's phi plus? Phi plus is just a function that measures, it's a function in the phase space that measures the signed distance to gamma plus. This normally hyperbolic picture tells you that as you go along more and more, you will approach gamma plus exponentially. So what you do is, after a little bit of fiddling with an averaging procedure along the flow, you're able to find a signed distance function, which doesn't just eventually get close to gamma plus, but just constantly, exponentially converges to it, period, in this sense. So this function, I personally took it from Wunsch-Zworsky. That's exactly the moment where we part ways with all the previous constructions on the problem. Because what we're going to do now is we're going to do this. We'll take this to operators. Board could use some absorption. So you quantize these two functions. You got your pseudo-differential operators. And then by standard pseudo-differential calculus, this equation leads to the following commutation relation. Plus O large of H square. Again, this is all only valid microlocally near the trapped set. This just follows from here. Now, what I can do now is I can go back to my equation here. My Q doesn't matter near the trapped set anymore. It's just localized away from it, so I'm going to throw it out. And then when I commute, I can see that I have this auxiliary equation. P minus I H W plus minus lambda U is equal to O large of H square, again, microlocally near the trapped set. Oh, sorry. Forgot the most important part. Theta plus U. You might be a bit confused as to why I do this. Well, what happened is I have an equation on theta plus U. And what this thing did, it bumped my spectral parameter up. Because the symbol here is bounded below by nu min minus epsilon. So if I'm above, so if the imaginary part of lambda is bigger than, say, nu min minus epsilon minus H, what happens is that this positive contribution outweighs this contribution coming from lambda, and you're essentially in the upper half plane where you know you have no resonances by integration. Well, it's not integration by parts anymore because it's microlocal, but by a more expected estimate. So then you see that theta plus U is O large of H. So here's your auxiliary equation. It just pops out of nowhere. Of course, if we go back to this conceptual case that I raised, you can see that here the restriction on the imaginary part is much more liberal than what I had in the gap. It in fact applies to the first band of resonances. Of course, here the first resonance state was the constant function 1. And in this case, a reasonable, so if we had this situation, the reasonable candidate for theta plus would just be differentiation along x, and the reasonable candidate for u would be constant function 1. So you know that the most shallow resonance states are actually killed by this theta plus operator. OK, so that's step 2. Now, you can see this, not only this will give you the gap, it actually also gives you information about the least decaying part of your wave in a way, about the way it microlocalizes. Now, step 3 is you have to use something called semi-classical measures. At least that's the way I do it. You can do it also without it, but that's the fastest way to do it. Namely, OK, I have my sequence of counterexamples. After extracting a subsequence, I can always make sure that my sequence converges to a measure in the following sense. So mu converges to some measure on T star M in the following sense. So for each observable, if I quantize, it will converge to the integral of the symbol over the measure. So that's a somewhat standard part of microlocal analysis that you can actually do it. You can extract a subsequence. And this measure has some favorable properties. So this measure really, it measures the way your solution concentrates. This measure, its support has to lie on gamma plus because of this statement, because of step 1, because your U is small outside of gamma plus. Then the equation there tells you that if I extract a further subsequence, and I assume that my my H inverse times the imaginary part converges to some number beta, which will have to be in my gap because that's the restriction on lambda, then I have conditional invariance with a 2 here for any open set. So what this tells me is that if I took my measure, it lives on gamma plus, if I took some set u here, I propagate it backwards along the flow, its measure will, well, decay or grow exponentially depending on what beta is. This way, you immediately can see why this upper half-plane estimate was true, because if your beta was bigger than 0, then your set would shrink. You know, I could take a whole neighborhood of k here, but your measure would grow, which is impossible. So this is one condition that we'll have to require. And finally, we have to use the auxiliary equation somehow. Of course, it's possible that I just wrote it, in a crazy tangent. So what does the auxiliary equation tell us? Well, it turns out that this O large of h, where is it? Here. It's my auxiliary equation. This O large of h situation is a little bit not enough to have invariance of the measure under the Hamiltonian flow of phi plus, which is the principal symbol. So if I worked a little bit harder here, I got, say, h cubed, then I could actually say that my measure has to be invariant along the flow of the symbol of this operator, which is this function phi plus. And if you look at the Hamiltonian flow of phi plus, what you will see, so this is on gamma plus, it's these lines which are transversal to the trapped set. So you got a measure which has a specified rate of exponential decay as you propagate along the flow. And across the trapped set on these trajectories, well, it's not going to be invariant. But what you can show using this is that it's going to be Lipschitz. So it's going to be this. So if I take a delta neighborhood of k, then this measure is going to be bounded by some fixed constant times delta. So that follows along the same lines as this proof, which is well, it's not a commutator estimate, it's just a commutator statement, which unfortunately I don't have time to write out. But the point is that these facts are enough to actually prove your gap. See, because you had your solution, it converged to a measure, it lived on gamma plus. It's invariant under the flow. Unfortunately, the measure doesn't need to be smooth or regular in any way. So what could happen is, for example, I could have a measure which is like a delta function living on k. And then the measure of the set under propagation doesn't have to decay exponentially too fast. So I would not be able to get my gap. However, what I have here, because of this auxiliary equation, my solution converges to a measure which is nice, Lipschitz, in these transversal directions. So now if I take some neighborhood of k, let's call this big neighborhood of ku, and I propagate it, what I see on one hand is this formula that I had before. And remember that my 2 beta is bigger than nu min minus epsilon, So this measure, as you propagate backwards, it cannot decay exponentially too fast, because the imaginary part of the spectral parameter doesn't let you do this. On the other hand, this thing is contained in a, well, some constant times e to the minus nu min minus epsilon t neighborhood of k. Because as you started here, when you propagate backwards, well, you know that all of your trajectories have to converge to k, and nu min is the convergence rate. So when you take this set, you propagate for a long time, you get a very, very small neighborhood. And then this transversal regularity gives you that this is just, well, just bounded by a constant times this. And then this is a contradiction, because here I know how fast my measure has to recede. This is not 0 by, again, a more or less standard propagation fact. On the other hand, the imaginary part of a parameter doesn't let me decay exponentially so fast. So this is, in 2 words, how this gap is proved. OK, well, thank you.